by the way, so there's going to be a homework that we assigned today, and it's going to be due not this Thursday, but the Thursday after this. Okay. And there is no lecture meeting this Thursday, and we'll arrange a makeup lecture another time. So we should talk a little bit about that instead. Are there any questions about anything at all before we get started? Okay. So if you go to the web and do a Google search on the author's name and the word ORMN, that's Operations, Research, Models, and Methods, you will find this website. So obviously I don't want to lose this. So this is the web page for the textbook. It has a lot of information. So some of the interesting things are, first of all, it has some testimonials. These are good things that people say about it. Seriously. So if you look at, so there's an introduction to the textbook and to the topic as a whole, and then there are these various sections, which are models, methods, computation, problems, and OMIE is just some subset of the textbook that's in there. So if you click on models, it takes you through a variety of models. So for instance, there's a discussion of what OR is. There's linear programming, network flows, integer programming, nonlinear programming, dynamic programming, and combinatorial optimization, which is what's relevant for our course. And then it goes on to stochastic stuff as well, which we won't do in this class. Okay. Similarly, if you go back and click on methods, it tells you various methods for solving linear programming problems and for flow problems and so on. Okay. A lot of these have Excel add-ins that come with it, so you can actually add the add-in and then use these methods and figure out how things work. There's a section on problems that discusses various problems that are solved, so you have access to these problems as well as to their solutions. And in general, this seems like a useful tool. So if you're working with a PC, you can actually go here and run pretty much everything that's on the website. I think the CD that comes with a book also has many of these things, so you may actually see it there as well. Yes?
Do they have a solution to any of the problems in the textbook on the website?
I'm not sure, but I mean, I assume that there is a large overlap between the problems they discuss and the problems in the textbook, because it's usually difficult to come up with new problems. So the answer to that, I believe so, but I haven't actually checked. So I'll probably add a link to this web page to our class homepage, but it should be easy enough to find for you. Okay. Let's see. Okay. Now about the course itself. So as I said, your graded homework 1 is available in my office, so you can come and pick it up from me. Homework 2 will be graded and will be ready fairly soon. Solutions to the first 2 homeworks are already on the web. They are in the coursework website. And I've also added a little detail to each of the lectures that we've discussed. In particular, I've assigned reading materials for all of the lectures we've had so far, reading materials from the text. So for lecture 1, there's some sections of chapter 1 that you're supposed to read and so on. And that'll be updated fairly soon so that we know what to read ahead of time. Okay, so let me actually illustrate a few issues involving the simplex method with some of the animations on the website. Okay, so here's the linear programming model. This is the one that we solved. And here's a nice picture of the feasible region, which is what I didn't have. So the region, the yellow region, is a set of all feasible solutions to this LP. And you can see that the corner points are this one, the origin, this one, x1 equals 0, x2 equals 5, this one, 5, 10, this one, which is 20, 5, and this one, which is 20, 0. And we saw already that the optimal solution is this particular point. Okay? Now this shows you how to first express the problem in standard form, which an exercise that you've already done. So you add 3 new variables. And then it also shows you the Tableau format, which we have not seen, but this is essentially the dictionary format, except that the equations are all written in a conventional way, so that all the variables are on the left-hand side and the right-hand side has only the numbers. So for instance, if you look at the first row, it says z minus 2x1 minus 3x2 equal to 0, which is the same as saying z equals 2x1 plus 3x2, which is the equation that we had. Likewise, if you look at this row, the third one, it reads x1 plus 3x2 plus x4 is 35. That's exactly what you have here. And the only difference between what we did and what is in here is that we rewrote this equation as x4 equals 35 minus x1 minus 3x2. And our way of doing things reflected the fact that we were viewing x1 and x2 as variables that are under our control, and x3 and x4, x5 are variables whose values are determined by the constraints. So visually that view is conveyed by the dictionary format, which is not the case with the Tableau format. But the advantage of the Tableau format is that if you actually want to solve the simplex method on paper, then you don't have to carry around all of these variables all the time because you're just operating on numbers. So you may as well just work with this set of numbers, which is a good thing. Those of you who learned linear programming most likely would have learned it this way. So the red entries here, I'm not sure if you can make out the difference in colors. So these entries are what's called the basis matrix. So these, this reflects the fact that for this particular equation, x3 is the basic variable. Similarly, for the second equation, x4 is the basic variable. For the last equation, x5 is the basic variable. All the non-basic variables are assumed to have 0 values, and the basic variables have values equal to the right-hand side. And as we go from one iteration to the next, you will see that the basic variables change, and you will see that the column corresponding to basic variables will always look like one of these columns. Okay, so let's actually continue. So this just tells you what the details are. So your textbook tells you, find the variable that led to the basis by selecting the column with the most negative value in row 0. So according to this rule, you will have selected x2 to enter the basis. And this tells you how to do the minimum ratio test, and you will see how to do the pivoting as well. So for instance, x2 will enter the basis, and you will compute the ratio. And when you compute the ratio, you always divide the right-hand side by those entries that appear with a positive coefficient in the Tableau format. Okay? And this one is the minimum, so that becomes the leading variable, and this becomes the pivot entry. Okay? Now, what that means is that you want to keep a 1 here, and you want to make everything else zeros. So that's the intention. And remember, the way we transform at one dictionary to the next dictionary, that accomplishes exactly this, that it's going to make this column 0, 1, 0, 0. And if you have to do this, then all the other columns have to change in a particular way. And this is done by a process called row annihilation or row reduction. I don't know, whatever you want to call it, but we've already seen this. Okay? So when I click here, that change is done. And we continue. So now we have to introduce x1 into the basis, which is the only negative coefficient. And so we can select, so this gives you the option of selecting anything you like. So we can select x2, this. So that's what we did. Now we could try to select something else, but this says that that's not allowed. You're making a mistake. So this is one way for you to learn what the right thing is. So we select x1, and again you could say this or this, which are all the wrong choices, but it lets you do what the right thing is. Right? And of course, again, when you click on the pivot element, so this is a 4. So for instance, this particular row, after I click on this, should look like 0, 1, 0, negative 3 over 4, 1 over 4, 5. And then you will do operations with it. And so that resulted in you're going from this point to this one. And now again, there's some entry with a negative coefficient, which is this one, and this is the only thing to do, and that's an optimal solution. So it's just exactly our example that we worked out in painful detail in class, spending a lecture, illustrated in a couple of minutes. Any questions about this? So, like I said last time, I think your textbook does everything in terms of tableaus, and you should feel free to use that if that's your preference. From the point of view of understanding why we are doing whatever we are doing, I think the dictionary representation is much better. That's my opinion. Okay. So this goes back to the same thing. Now, I also want to show you a few other things. So we just went through this primal simplex method. I want to show you alternative selections for the entering variable. And for this, so I go to view source.
Just click somewhere here.
Here?
Yeah, here.
Okay. View source, and I search for SW.
Yeah, exactly.
Okay. Okay, wonderful. So remember that in our example, we followed this little rule that was set, right? Which said always enter the, if you have many possible choices for the entering variable, pick the one with the most negative coefficient. Now that's like saying, pick the one that's going to give you the largest profit per unit change. But of course, that may not always be the right thing to do. And it may not always be the obvious right thing to do also. For instance, you may change X2, pick up $3, but your allowable increase might just be 1. In which case, your potential, the improvement that you make is only 3 in that step. But maybe if you introduce X1 into the basis, even though you get paid only 2 for unit increase, you may actually be able to increase it by 10, in which case you make $20 in that step. Now ultimately it doesn't matter, because eventually you will get to the optimal solution. But there is a, there's just as compelling an argument to be made for choosing an entering variable such that its coefficient in the zeroth row times the allowable increase is the largest possible. So in other words, for every possible choice of entering variable, you compute the product of its coefficient and the magnitude of the increase. And whichever gives you the largest possible value there, that could be a choice. Of course, you can cook up instances where that is not the best possible choice of entering variables, and so on. So here's a little demonstration of how things would change if you pick something else instead. So if you recall, when we picked x2 to enter the basis, we went here, and then there. So we did 3 iterations of the simplex method. If you pick x1 instead, then you're going there and going up. So, as you can imagine, if you pick x1 to enter the basis, you would go from the origin. Remember, x2's value is held at 0, and you would increase x1 as far as your constraints permitted. So you would go from this point 0, 0 all the way until the point 20, 0. And from there, the only choice that you have is to increase x2, and you would go here. And so you get to the optimal solution in two iterations, as opposed to 3 from the other choice. Now the difference between 2 and 3 may not be much, but if you scale things by 1,000,000, then it matters, right? So it is worthwhile trying to understand what rules are good and which ones are better, and so on. And unfortunately, the answer is that there is no unambiguous choice of the best rule. So in some sense, you just have to be lucky. Now, there's a lot of empirical work showing that the steepest increase, so looking at the product of the coefficients and the magnitude of the change, that rule is very good. But again, it's not good in the worst case. So if you employ that rule, I could construct an example where that rule is not so good. But it turns out that in many natural problems, that rule does pretty well empirically. Now, similarly, so this talks about, so this just shows you the 2 different ways of reaching the optimal solution. And it says something that's exactly what I said. So I just showed you something about ties for the entering variable. So one could have ties as a choice of leading variable as well. And so for that, I want to show you something now. So let's look at this example, except that there's another constraint. Okay? So there's a constraint C4, which says x2 should be at most 10. Now let's actually see what happens. And we'll understand one additional difficulty that may come about. So this is the initial tableau. As before, you add a slack variable for every constraint. So now we have 4 slack variables because we have 4 constraints, all less than equal to constraints. And our basis is going to consist of 4 elements because we have 4 equations. So initially, again, we let x2 enter the basis. This is the minimum ratio, so we do this pivot. And now but there's only one choice, which is x1. And then x1 enter the basis. And when x1 enters the basis, there's a tie for the leading variable. So two different variables achieve the minimum, and that's a problem. So why is that a problem? Well, for one thing, now you have to make a choice in your method as to which of these you're going to treat as the one that leaves the basis. Okay? If this tie were between two rows that are not the minimum, so in other words, if you had a 5, 20, and 20, then that really doesn't matter because your choice is still unambiguous. The row that achieves the 5. But because you have two things achieving the minimum, now you have to pick one. And again, let's pick anyone. Let's pick this one. So if we pick this one, what's going to happen? Well, we are going to move, and we move from this point to this point. But when we move, remember that because there were two rows achieving the minimum, one of the new basic variables is going to become 0. So in other words, when there's a tie for the leading variable, when you do the pivot, so when you pivot, you will have two variables that become 0, one of which will be chosen to be non-basic, and the other will still have to remain basic. So it will remain basic, but at 0 level. Okay? So far in our examples, we've seen the non-basic variables are at 0 level, and all basic variables have positive values. So here's an example where we are at a solution where some basic variable has 0 value. Now, why is that a problem? It is a problem because when you are at such a simplex tableau, your next step, you may not actually make any improvement. Now, how is that possible? So remember that the magnitude of improvement always comes from looking at the ratio of this to some coefficient here. Okay? So if this row is going to be involved in the minimum ratio test, then the magnitude of improvement in this test is going to be 0 because its right-hand side is 0. So this means that you're going to do one simplex iteration potentially without increasing your objective value at all. Okay? Any questions about this? So this is called a degenerate pivot if you don't make any improvement. Let's actually continue. So, for instance, we are going to let x3 enter the basis, and notice that here something nice happens. We let x3 enter the basis, but then only those with positive coefficient here will enter the minimum ratio test. And so even though this is 0, it does not enter the minimum ratio test, so we are not affected by the problem that I just mentioned. But if this coefficient were plus 0.25, for instance, then this would be part of the minimum ratio test, and you would have a 0 here, and the ratio will be 0. Right? 0 divided by this positive value. And in that case, your next step, you will still have degeneracy. You will not have moved at all. You will just do what is called a change of basis. Whereas in this step, fortunately for us, this had a negative coefficient, and therefore it does not enter the minimum ratio test, so our next step will not be degenerate. Okay? So let's continue. So this achieves the minimum, and you're done. So let's actually do this. Suppose we enter x1 into the basis, and instead of picking this one, we choose this as a leading variable. I'm sorry. We choose this as a leading variable. Then when we do the pivoting, we have a 0 here. Okay? And again, this is a degenerate solution because, so any solution in which a basic variable occurs with 0, is at 0 level is a degenerate solution. Now certain degenerate solutions might be a problem, and certain degenerate solutions are not. The previous degenerate solution that we had, we could pivot further because the degeneracy didn't affect our improvement in any way. But here, the situation is going to be different. So here we let x1, x3 enter the basis now. But then you see that this coefficient here is positive, and therefore it becomes part of the minimum ratio test, which means that we are going to do one iteration, making no improvement to the objective value. In fact, we are going to do one iteration without physically moving from this point. The reason is, so this row says the following. If you enter x3 into the basis, you're going to make an improvement of $2 for every unit change. Okay? So if you increase x3 by 1, your objective function will increase by 2. That's what this is saying. Unfortunately, what the minimum ratio test is saying is that you cannot increase x3 by anything. x3 has to be 0 for you to stay feasible. Okay? The reason is that at this point, you don't have just 2 active constraints, you have 3 active constraints. So typically, every point is determined by, here is determined by 2 constraints. Whereas here you have a point determined by 3 constraints. And the third constraint forces you not to move at all. So while it is true that you get a benefit of $2 for every unit increase in x3, to stay feasible, you are forced to keep x3 at 0 level. And therefore, you don't move. What you do, however, is change your set of basic variables. So right now, x1, x2, x4, and x5 are your set of basic variables. And you're going to now, after you introduce this into the basis, you're going to call another set of variables basic. Okay. So x1, x2, x3, and x5 will become basic now. And this is the other solution that we had. The first route that we took, we were here. So now you continue, click on this. Again, the nice thing happens that even though this is degenerate, it does not participate in the minimum ratio test, so we will make progress and we'll reach the optimal solution. Okay. So the summary is that when you have a tie in the minimum ratio test, your next solution will always be a degenerate solution, meaning one of the basic variables will have 0 value. Now once that happens, there are 2 possibilities. Either you get out of degeneracy in the next time step immediately. That'll happen if the basic variable with 0 value does not enter the minimum ratio test. So the fact that you are at 0 level does not affect you in any way. So that we saw an example of that first. Then it's also possible for that variable to enter the minimum ratio test, in which case you will do what is called a degenerate pivot. And that means you stay at the same point, but you just change your set of basic and non-basic variables. And the reason why that's possible is because you have basic variables with value 0. So in other words, out of the 6 variables, we should have only 2 of them 0. But if you have 3 of them 0, then you get to pick which of those 3 you want to call non-basic. And that generally leads to problems. So once you recognize that it's possible to do a simplex iteration without making any improvement, then the following should worry you. That maybe you start with some set of basic variables. You do a degenerate pivot. You go to another set of basic variables without making any improvement. So you're staying at the same point. Do another degenerate pivot. You keep on doing this, and then at some point you go back to the basis you started with. So you start with some choice of basic variables B1. You do an iteration, a simplex iteration, you go to B2. Another simplex iteration, you go to B3. And another one, you go back to B1. All the while staying at the same point. And if this happens, and if you use deterministic rules to resolve ties in entering and leaving variables, then you're going to do, after B1 you'll always get B2, after B2 you'll always get B3, you go back to B1, you keep on doing this without getting out of that point at all. Okay? This is called cycling. And simplex methods with pathological choices of entering and leaving variables could actually cycle. So that's bad news, because you have a method that at least works in some little examples, but actually it has the potential of cycling, meaning examining bases that it examined before and therefore not making any improvement at all at some point. So a few lectures ago somebody said, well, there are only finitely many bases and therefore this method should always terminate. And unfortunately for this reason, that is not always true. So if there are finitely many possibilities, you will always terminate as long as you examine a distinct possibility each time. But if there's a possibility of revisiting things that you've already examined, then of course you may be locked in an infinite loop. That's the bad news. The good news is that there are simple rules that avoid cycling, always. So one such rule is called Bland's rule. It's named after Bland, who discovered it. And it says the following. Order the variables in some way ahead of time. For instance, you could just order them according to their subscripts. So suppose we use the subscript as the order. So x1 always is before x2, 2 is before 3, and so on. Then whenever you're faced with a tie, resolve the ties based on the smaller subscript rule. So for instance, if x1 is a candidate for entering the basis, you will enter x1. If x1 is not a candidate but x2 is, you will enter x2. So at any stage you will enter xi only if all smaller values, all smaller subscripts, variables, are not candidates for entering into the basis. So whenever you have a choice, go with the smaller subscript. Similarly for the leading variables. If you do that, you will never cycle. This is a very clever, very elegant argument that we won't discuss in class, but I'm sure I can point you to a treatment of this and a proof of this fact elsewhere. But for our purposes, it suffices to know that there are ways of avoiding cycling all the time. Now, this is not going to avoid degeneracy. You may still do baseful iterations, but you're never going to cycle. So you may still go through a sequence of 100,000 iterations with no improvement. The only guarantee is that you won't cycle. You won't go back to the same basis.
It's like coming into a maze and always keep on the right.
Something like that, yes. So, I mean, that's sort of the way it works also. That you can show that somehow you always make, even though you don't make improvements tangibly in terms of the objective, you can never revisit the same basis. And therefore, that would avoid cycling. Yes?
So does economically guarantee that it's, for example, in this example, it couldn't be more than 6 factorial or not?
Well, so the guarantee is it wouldn't be more than the total number of bases you have. because you never re-examine a basis that you visit. So the worst case guarantee is if you have n variables and n constraints, the worst case you will examine n choose m possibilities. That will be the number of iterations. Yes?
So taking the variable with the lower coefficient at the entry one will warrant that we do not subscribe.
And for the leading variable as well.
Okay. And if we do what I said before, we take the variable with the product of the coefficient.
Right. So if you want to use other, so this is a rule that says entering and leaving, use this and you won't see any sideways. Now, if you want to use a different strategy for entering variables, then there are other ways to avoid cycling. This particular rule will not work. Yes?
So it only happens like when it's like two ties.
Right.
Is there any way to avoid this tie?
Is there any way to avoid this? Well, you could think about perturbing the right-hand side by a little bit, right? Instead of 5, you could say 5 plus 10 to the minus 9 or something. Now you have to be very careful when you do these perturbations because you want to make sure that they don't create. In other words, you still want to solve the problem that you started with. And if the perturbations start mattering, then you're solving the wrong problem. But there are ways of, there's a science of, how you would perturb these coefficients so that you avoid this. Loosely speaking, this is called the lexicographic metric, and that's another way to avoid cycling.
Should you do an example of this using the smallest?
The smallest subscript rule. So, for instance, let's actually do this. Okay. So this is just the conclusion. Let me start again. Okay, so for instance, so here, for instance, I could let x1 enter the basis or x2 enter the basis, right? I would introduce x1 into the basis. Now, it doesn't have to be smallest subscript. It just has to be an order that's determined ahead of time. So, for instance, my ordering of the variable could be, it could be 6, 2, 1, 3, 4, 5. I could use this order. A smaller subscript, I said because it's just convenient this way. But as long as you break ties with respect to a fixed order, that you don't keep changing as you run the algorithm. So let's actually do this. So consistent with this order, the first choice that I have is x2, right? Because x6 is already a basic variable. So here, the only choices I have are x1 and x2, and 2 has priority over 1, so I would let x2 enter the basis. So let's enter x2 into the basis. And here there is no tie, so I have to let this. We do the pivot and continue. And now there's only one choice, which is x1. So, but now there's a tie. Okay? There's a tie, and either x4, so I could let x4 be the leading variable or x6 be the leading variable. Now this order says I should use x6. I click on this and I continue. So here again there is no choice, and here again there is no choice. So whenever there's no choice, you just pick the one that you have. Whenever there is choice, so here again there's no choice, and is again the only choice. So you click again. You've got to get to the optimal solution. Now this isn't much of an illustration because first I have to show you an example where cycling actually occurs and then show you how that's avoided by this rule. Now cycling, while it could occur in the worst case, it's not actually very common. So there's a question about other entering rules. So if you use that, and then there is a chance that the method will cycle if you use some rule other than this, but it's not common enough. In fact, it's very difficult to construct instances where the method cycles. So to tell you a little bit about it, I think in the 60s, finding an example itself was difficult. People couldn't prove that cycling cannot occur. So they suspected that maybe it does occur, but it was a while before somebody actually constructed an example. The first example was monstrous. It was pretty big. And then over time, people have simplified it. I think the smallest one probably has 6 variables or so, and cycling is over 6 iterations. And there's some recent work that constructs somewhat better instances where the cycling can be shown in fewer iterations than 6. But if you look at any textbook that discusses cycling, it would have sort of the same 6 iteration examples, which suggests that it's not that common to observe cycling. Now, while it is not common, it could occur. So if you're using this method in a sensitive application, for instance, where you have to guarantee accuracy, it has to work 100% of the time, then you don't want to have a method that may cycle. Okay? So you may get around this by doing other things. So for instance, you could use your favorite pivoting rules, and if you make no improvement at all for 100,000 iterations, then maybe you suspect that there is some cycling going on, and from then on you start using some rule like this until you get out of that point. And then you revert to your favorite pivoting rules. So there are many, many ways of recognizing that maybe we are cycling and then getting out of it. Okay? Okay, so any questions about any of these concepts? Okay. Now, we already said that there are no unambiguous best rules for entering and leaving variables. If you want to avoid cycling, then you do something like this. But actually, one may wonder, are there good pivoting rules for the simplex method? And so, let me tell you a little bit about this. It's probably discussed in your textbook only to a minor extent. And this is an issue that's not so important for this particular class, but I think you should be generally aware of some of these issues. So, as we said, by looking at a picture and then by abstracting some of the things that we observe, we said the following, that every linear programming problem that has an optimal solution has an optimal solution at an extreme point. And an extreme point is the same as a basic feasible solution, something in which if you have m constraints, you have m variables that are basic. And therefore, you can examine all possible bases, which are n choose m. And then by checking the objective value at each of those points, you can determine the best one, or you can determine a best one, and that's an optimal solution. Okay? So that is one way to solve a problem, which may not be particularly good in large examples because you could have many, many bases. So the natural question is, what does the simplex method do? Does the simplex method do any better? It seems like we're using a lot of clever ideas. So does this solve the problem much faster? Is the question clear? Is it any better than looking at all possible solutions to your problem? And the answer is, it depends on what you mean by any method. As you know, the simplex method has, it's not a method, it's a family of methods because there's a choice when you have many variables to enter the basis, and there's a choice when you have multiple variables that leave the basis. And depending on how you make these choices, you get a different method. Now it turns out that for many known pivoting rules, there are instances where the simplex method goes through pretty much every corner point before getting to the optimal solution. In other words, for many pivoting rules, including the ones that we discussed in class, there are examples where simplex method takes 2 to the n time. And these are examples which are hypercubes, which have 2 to the n extreme points. So in the worst case, we don't know of any pivoting rule that solves linear programming efficiently. Efficiently is in a sense that doesn't examine everything. That the running time of the simplex method somehow is not very good in the dimensions of the problem. So for all known pivoting rules, there are examples in which the simplex method takes time that is exponential in the size of the problem. To specify a linear programming problem, I just have to tell you what the constraints are. Basically, I just have to give you this initial tableau. Okay. You can see that that's not too much, right? It has, I think, n times m numbers plus some extra. But actually, the simplex method takes time that's not any polynomial in this quantity. It could be exponential in this quantity. So that's one bad news. Well, there's always the possibility that somebody clever enough might come and find a pivot rule for which such an example is not possible. So we don't know the answer to that. So such good rules may exist, but a lot of clever people have spent a lot of time on this issue, and so far they've not succeeded. Okay. So that's in the worst case. Now, typically, simplex method runs very efficiently. So it works very well on pretty much most classes of problems. There are other ways of solving linear programming problems, and for most problems that we see in this course, and for many, many real-world problems, simplex method is competitive with these more efficient, these methods that are more efficient in theory. So simplex method has lots of other good things. So for instance, when you want to do re-optimization, so you solve a problem, you have an optimal solution, and now you make a small change. Re-optimizing is very easy with the simplex method, substantially easier than with these other kinds of methods, which are called interior point methods. So even though we don't know of any pivoting rule that guarantees an efficient solution in the worst case, the method is attractive enough and it's simple enough that it can be taught, and that I believe ought to be taught. You ought to understand it well enough. This is probably the most commonly used method to solve linear programs, except in research labs where people are working on much more efficient codes that are based on other methods. Okay. So to summarize, in the worst case, simplex method, no known version of it is efficient, and most known versions of it have bad examples. So it's not as though you don't know the answer for particular pivoting rules. For many pivoting rules, people do know that it's bad. Empirically, this method works very well, and it has lots of advantages over other methods that it's worth implementing and studying. Okay, so this is a method to try first, and if it fails somehow, then you resort to other things. Any questions about this? Now, finally, I want to show you an example that deals with initializing the simplex method. So I wrote down, we addressed this towards the end of the previous lecture, but now I want to show you in detail how and why this works. Okay, so let's again go to methods, linear programming. It's called the two-phase method because the first phase is when we try to find a feasible solution to our first problem. The second phase is when we find the optimal solution. Okay, so again, this is the same problem that we started with, except that there is a fourth constraint, C4, that says this portion below is infeasible. Okay? Now, before, we had a particularly easy solution, right? Everything here was feasible, so C4 didn't exist. Therefore, we could select the origin as our initial feasible solution. So this corresponds to viewing x3, x4, and x5 as basic variables, x1, x2 as the initial set of non-basic variables which assume value 0. And that was feasible for the original problem, so we could get the method started. So the problem here is that 0, 0 is not feasible. Okay? So you have to work to find a feasible solution from which to start. Does everyone recognize the difficulty? If this is an issue, please ask me so we can go over it in more detail now. Okay, good. So first we convert it to equations. Okay. And so remember that the last constraint actually read the following. x1 plus 1.5 x2 was at least 10. Okay? So to convert it to equality form, we would say, we will take this constraint, x1 plus 1.5 x2 is at least 10. And we would say x1 plus 1.5 x2 minus x6 equals 10. So this is how we would convert this equation to a standard form. Because this is greater than equal to, you subtract the surplus variables. Remember, all our variables have to be non-negative. And the problem with this is that if you want to take x1 and x2 as 0, then x6 is forced to assume a negative value. And that's why the problem is infeasible. So what we are going to do is the following. You add another variable with a positive coefficient. It's called A1, this equation. And A1 occurs with a positive coefficient, and you're going to think of x1, x2 as still non-basic. You're going to think of x6 as another non-basic variable, and A1 is going to be a basic variable with value 10. So the idea is that we are going to start with a solution that is feasible if you replace this inequality not by this, but use this instead. Okay. And as I said, magically the problem doesn't go away. What you've said is, even though I want to find values of x satisfying this equation, I'm going to now not worry about it. I'm going to instead find values of x satisfying this equation. Of course, if I had this equation, I could use A1 as a basic variable here, and everything would be fine. So I would let x1 be 0, x2 be 0, x6 be 0, and a1 be 10. Now the problem is that that solution doesn't satisfy the equation that you were given. It just satisfies an equation that you've cooked up. So you're not solving the original problem. So this is not surprising because, of course, you can always write your favorite equation and pretend that you're solving that instead. But this is not a pointless exercise because what we'd like to do is somehow start from here and work our way to finding a solution that satisfies this equation. So if you start by satisfying this with a1 equals 10, and if you want to satisfy this, then somehow you want to make a1 0. Okay? If a1 is made 0, then any value satisfying this equation with a1 0 is really satisfying that equation. Now in terms of a picture, what's really happening is that this blue region, which is actually infeasible for the problem, you are now making it feasible by adding this a1. So what you're really saying is, okay, I know that the origin is not feasible, but I'm going to make it feasible. I'm going to expand my feasible region. But I'm going to solve a different problem such that solving a different problem over this expanded feasible region optimally would put me in the feasible region of the original problem. Okay, so this is the idea. That you're given a problem such that you're not able to start the simplex method. You expand the feasible region so that the simplex method is easy to start. But then tweak your objective function so that you start the simplex method and that when you solve this objective function optimally, you get a starting point for the original problem that you started with. So the first objective function of the problem that you solve is called a phase 1 problem, and at the conclusion of phase 1 you will have one of two possibilities. You will either say that the original problem is infeasible and therefore we just stop, or you will find a starting solution for the original problem and then you'll continue doing phase 2. So remember that the phase 1 objective is to minimize a1, which is the same as maximizing negative a1. So you're going to first maximize negative a1 subject to all of these constraints where a1 appears here. And if you find, at optimality, if you find a1 equal to 0, then you are in effect finding x value satisfying these constraints. The last constraint without the a1. And that is a feasible solution to the original problem. If, on the other hand, phase 1 terminates and you have a1 strictly positive, then it's easy to check that there is no solution to the original problem. Because a solution to the original problem, along with a1 equal to 0, would give you an optimal solution to the phase 1 problem. Okay, so if the original problem had a feasible solution, then the phase 1 part had to end with an objective value 0. Therefore, if phase 1 terminates with a1 strictly positive, the original problem cannot have a feasible solution. Okay? So again, in terms of the picture, you're going to start here, and you're going to minimize a1, which is the same as saying, if a1 is 0, then you will somehow end up in this yellow region here. If you optimize and somehow end up in the blue region, then a1 has to be strictly positive. Now you can continue. I guess, we do anything we like. So you're going there, and remember that a1 is still positive. Then let x1 into the basis. So now a1 becomes 0. Yes.
Question.
practical steps to start manually the solution to find a feasible solution.
Is it possible to somehow just find a feasible solution?
Yes, manually.
Manually? Well, the answer is, how would you do it?
You can maybe consider at any point the solution of the system of the equation.
So you have to, so in other words, if I give you n variables and n equations, then you have to sort of figure out, which variables are going to be basic in your feasible solution. So pick some set of m, and then solve, and hope that you will get a feasible solution. And if you don't, you have to pick another set of m variables and solve. So in other words, by trial and error, you could find a feasible solution. But you cannot actually say, this is a feasible solution. Right?
Yes, but if you look at the picture, for instance, the point that
if you look at the picture, well, I can see that there are feasible solutions, right?
Yeah.
But if you look at the picture, you can even see optimal solutions.
Yes, of course. But my point is that each point is the intersection of two lines.
Right.
That's the intersection of two hyperplanes.
Mm-hmm.
So in order to get the coordinate of that point, you just need to solve the system.
Right. You just need to solve a system of two equations and two unknowns in this example.
Yeah.
Okay? But you have to figure out which two, so certain sets of two equations would give you solutions with negative values. Okay? So you have to figure out which of the two you would pick. And if I give you a problem that's actually infeasible, you have to go through every possible choice before you conclude that it's infeasible. Yeah? So it's a good question, but this is the reason why it doesn't work. So you have to use trial and error, and if you're using trial and error, you may as well solve the LP by trial and error. Why just setting for a feasible solution?
And also just mention that the idea of solving a solution doesn't always give a feasible solution, because the point that is not always in the feasible.
That's exactly right. In fact, in your homework or in one of the lectures, we saw that even though we had 5 equations, we didn't get 10 corner points. We got only 5 that were feasible. So, as I said, if I give you a problem that's infeasible, then you will have to try every possible choice before you conclude that it's infeasible. Whereas this is a more systematic method. Now, based on the remarks that I made just a little while ago, it may be that to solve the phase 1 problem, you do end up trying every possible choice. The simplex method does. The simplex method, by and large, would be cleverer than that. Okay, so after a couple of iterations, you end up at this feasible solution. Now, A1 is non-basic, so when you continue, this solution is an optimal solution space for phase 1 because you have A1 equal to 0. Now you can continue by replacing the first row with the new first row. Okay? So you're going to get rid of A1 and express your objective function in terms of the non-basic variables of this tableau. Now you did this exercise in homework 2 in the last problem, where I told you what the basic variables were, and the objective function had a basic variable that you replaced. Okay? That's what you have to do here to set this up so that you can apply the simplex method starting here. Any questions at all about the two-phase method? Okay. Now, there is another way of solving, of initializing the simplex method, which is the following. So let me go back to the original problem. I could say, I'm going to still add this artificial variable, but instead of doing 2 phases, I'm going to do the following. I want to maximize 2x1 plus 3x2, and I'm going to do minus 10 million times A1. So I'm going to solve this problem, except that my objective function is 2x1 plus 3x2 minus 10 million A1. So what do you think would happen? you would get the same thing because it seems like 10 million is way too big compared to any of the numbers involved in any of this. And if you set A1 to be strictly positive, even by a small amount, you're going to get penalized heavily for that. So somehow you would end up setting A1 to 0. So the difficulty with this is precisely the following: is how big a number you should pick as the coefficient. Maybe minus A1 would do it, or maybe negative 10 million is still not sufficient. So it's hard to determine how big a coefficient you should, a penalty coefficient you should have before A1, so that you get what you want, so that you get a solution to the original problem. So this is called the big M method, because you're saying, instead of this objective, I'm going to do 2x1 plus 3x2 minus m times the sum of all the artificial variables. The A's are called artificial variables. So you can analyze the sum of artificial variables by a huge number m. And if you pick m large enough, then this would do it. You would solve the original problem. And the difficulty is that it's hard to determine how large is large. So you may have to do this a few times before you're convinced that the problem is feasible. So again, if I give you a problem that's actually feasible, somehow you can work with some value of m. If it doesn't work, you can double it and keep on trying until you get a feasible solution. But if the problem is actually infeasible, then when do you stop this? How big a value of m should you pick before you're convinced that the original problem is actually infeasible? So no matter how large your m is, A1 is still going to be positive. Because of that issue, the two-phase method is sort of preferred, because it doesn't get into all of those problems. Okay, so just to summarize where we are, in terms of your textbook, we discussed essentially chapters 1, 2, and 3, except for a couple of sections in chapter 3 that we revisit a bit later. As I said, the coursework page for the class is updated, and it has reading associated with every lecture. And I'm going to update today's lecture right now. Now, in the next lecture, which is on Tuesday, we are going to start duality theory and sensitivity analysis. These are discussed in chapter 4 of your textbook. And the main idea is that you start with a linear program. How does the objective value change as certain parameters of the LP change, certain data changes? So we want to understand the way the optimal solution changes when we change the right-hand side or when we change the objective function coefficient of a variable and so on. And we also want to understand what dual linear programming problem is and how it's related to the problem that we are solving. So this will take up the next 2 or 3 lectures, after which we will conclude a discussion of linear programming. Okay? So that's the immediate lecture plan, and I'll see you in class on Tuesday. So this Thursday there's no lecture, no office hours. The homework will be assigned today, and I'll send out an email to the class.